for those of you watching this, don't skip class. Cool. Thank you to those of you who showed up. Okay. Today, we're going to talk about membrane transport. Hopefully you watched the Ed puzzle. Membrane transport. So if you did watch the Ed puzzle and you already took notes on it, you don't necessarily... Like, that's why I put it on the remind. I recommended, like, if it were me, yeah, I blew up your phone a couple times. If it were me doing it, I would take all my notes while watching the Ed puzzle. Write down what I feel is important, what's not, blah, 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 blah. That way, when I come to class, I can just kind of sit back and listen. And if we talk about something in class that makes more sense, or that we didn't talk about on the video, I can write that down. Or if we say something in class that makes more sense in the video, I can write that down. That way, I'm not sitting here frantically trying to write everything down in class. The same thing would happen in college. I'd print my lectures and I'd go over them before class, and then that way during class I'd just take the notes on what the professor was saying that wasn't on the PowerPoint. That way you're not just trying to write down what's on the PowerPoint frantically. It's just for future reference. Okay? So membrane transport. There's two big categories of transport. I'm just going to talk about one of them really deep today, and the other one I'm just going to introduce it just to kind of give you a brief overview of it. And we'll talk about it again later. So the first one we have passive transport, and we have active transport. Passive and active. If I'm talking active, and let's say I say this kid was really active, what does it require if you're active? You're using a lot of what? Energy. So active transport requires energy. And energy in the form of, when we talk energy, we're talking ATP, adenosine triphosphate. Okay? And what the heck? If I'm also doing active transport, I am moving stuff. Ooh, why is it tweaking out? Moving stuff against concentration gradient, or moving stuff from low to high. So pretend at lunchtime, this little passageway between the science building and the fence. Have you guys ever tried to walk towards the Spanish buildings right at the beginning of lunch? It's kind of miserable. Everyone and their mother is trying to walk towards the lunch lines, and you're trying to walk against the opposite way. It's almost like you have to try and run there and duck down and run like an NFL running back, something like that. You're going against the concentration gradient. You're going against the flow of things, or it's kind of like a salmon swimming up the river. It's going to use a lot of energy to do that. So moving stuff from low to high, or we also call this against concentration gradient. If you've heard the term gradient before, it means going from high to low on something. So for instance, a lot of times you hear that term in art. The gradient means you're going from dark to light, or from one color to the next. So how I would draw this if I wanted to make a visual of it, let's say I've got this. Is that ball going to roll itself up the hill? No, it's not. What's going to be required for that to happen? Energy. So if I want this ball to go up the hill, I've got to input energy to it, and the energy that we use is in the form of ATP. Okay? I didn't hear you answer it, Josh. I thought it was Miguel answering questions. I'm like, Chief, you've already had this class. Yep. Adenosine triphosphate. That's the energy molecule that we use in our body. So if anything we talk about in this class where we talk about it requires energy, that means it requires ATP. That's actually a very good question. ATP equals energy. It's adenosine triphosphate. Okay. That's everything with active transport. We're going to talk about that more at a later date. But now we're going to focus on passive transport. So if passive is the opposite, what do you think passive is in terms of energy? Does it require it or not require it? No energy required. That'd be like if you were a fish and you're just in a river, you're just like, I'm just going to go with the flow of the river. I just stop swimming and you just let the river take you. Or if you're going with everyone that way, it's like there's so many people you could just almost not even walk, and it's just going to carry you along. It's just like let yourself go, and the crowd will carry you. Okay, so no energy is required. It's moving from high to low. Moving from high to low. And so a lot of times one of the biggest ones we talk about for this is diffusion. And we talked about diffusion when we talked about vinegar. Remember when we had the cubes? In the beginning, if I just took a straight cube that we had soaked in water, how much vinegar is in that cube? None. But what if I soaked it in pure vinegar? Where's the most? Is it outside of the cube or inside of the cube? Where's the most vinegar? Okay, most vinegar is on the outside of the cube where it's pure vinegar. And what did that vinegar start to do? Did it move into the cube? It did, because there's no vinegar inside of the cube, so that vinegar started to diffuse in. It didn't require any energy. Another way to kind of realize passive transport, which happens all the time, and you may not realize it, when people walk in here, a lot of times one of the very first things they do is they go to see what it smells like, because they never know what you're going to get when you walk in here. Exactly. Sometimes it's pleasant, sometimes it's very unpleasant. But one of the main things we have is that right there. All right, you may be sitting way over there. If I were to start that thing up and you're like, I don't smell anything. But Josh is over here. He's like, man, this is strong. Like, can we turn this off? It's giving me a headache. And so what happens is it starts to diffuse out. So where its highest concentration is right there. And over time, it's going to start to spread out and spread out and spread out. So in the very beginning, it's very strong right there, and it starts to spread out until it's evenly spread out across. It requires no energy to do that. There's something that we deal with almost daily that also does this, and you do it naturally. You know what it is? When you fart. Oh, it's not. Girl, you act like you don't fart. Okay? So, let's say I'm sitting here, and I said I farted. Yup. If I just said, yup, I farted. What's the first thing you would do if I said I farted? Mentiroso. You'd go... Oh, you're a liar. If I said I farted, you would not just get up and leave. The very first thing you would do is you would want to verify it. Okay? Yep. So, you would try and verify it, and depending on what I ate in my diet recently, if I had protein farts with whey protein, those are the worst. Okay? I would say that, and they'd be in the back, and they'd do the same thing as these guys up here. Hold on. Thank you. All right. And I would let one loose. All right. You back there would go, I don't smell anything. And they're up here gagging and dying up here. Okay. And then a couple minutes later, I just keep on going to my thing. And all of a sudden I look in the back and all I see is you guys going. I smell it now. And my mouth was open. Okay. Because what happened at the very beginning, where was the concentration very, very, very high? Right here. All right? And then, over time, it's spread to the low concentration because passive is moving from high to low. Over time, it's going to spread out naturally. Doesn't require any energy. All right? And so that's what's going on. A fart is passive transport because it's going to spread from high to low, and it doesn't require any energy for that thing to spread out. Sometimes you might put a little energy in there for it to spread out faster. For instance, if you fart thinking it's not going to smell and all of a sudden that one sneaks up on you and it does, you might or try and secretly fan it out, all right? But naturally it would spread itself out. All right, enough fart talk. Let's talk about, so if I were drawing this, how it would look. It's a ball rolling down a hill. Requires no energy. It's going to go that way anyways. It's not going to require any energy.
You do eating?
The party?
Yeah.
No.
You're looking around like it seems like you did.
Oh no, I'd be proud. I'd admit it. All right. So the big topic we're going to talk about one big topic for passive transport today. It's osmosis.
You wrote that really ugly.
I'm going to be nice and not say anything.
Say it.
Nope. My mother said if you can't say anything nice, don't say anything at all.
Really? I never thought of it before.
Wait, is that from Matilda?
What?
That word.
Osmosis? It is a very big biological term.
What is it from Matilda? She said that.
There's also a whole movie called Osmosis Jones.
I think she did.
On that note, with Matilda, did you know her parents were like, her mother was dying of cancer at the time, and so Danny DeVito and his wife took her into their his house to like stay with them while her parents were in the hospital and everything. And I think it was Matilda. He got an early release copy of that so her mom could see it before she passed away. Like, from what I hear, Danny DeVito's actually a really, really, really good person.
This is in real life.
Yes,
I thought
in
it was
real.
a movie.
No. In real life, like Danny DeVito, who plays the dad in Matilda, and the mom, like her mom in real life was going through chemotherapy and everything, and their parents were in the hospital all the time for that. And so Danny DeVito and his wife took her, the girl who plays Matilda, in while that was going on. And yeah, he got an early screening of it so the mom could watch it before she passed away, like to be proud of her daughter.
It's like in real life, this guy.
Yeah. Yeah. All right. Osmosis. So the osmosis is the passive transport of water from high free water to low free water. And no, that doesn't mean like, do I have to pay for my water? This is America. I don't gotta pay for my water. And you might be wondering, what the heck are you talking about free water? Trust me, niños. Cálmate. I shall show you. Okay, you guys got this? All right. Time for arts and crafts time. Okay, so let's say I've got a container. And in this container, I've got a cell. Let's say that's my cell. So I'm going to draw a couple things for this. And in this, I'm going to say I've got a water molecule. And I've got this round circle, which is going to be solute. That's thinner. Okay, solute, which is going to be stuff like sugars and salts. What the heck is tweaking out on my pen? Looks like I'm writing in Arabic. Okay. So it's going to be stuff like sugars and salts. Then I can also have... So I'm going to have a couple other words that I have on here. So if you see just this... Ooh, that's that water. It's going to be a free water. And if you see something like this, it's going to be a bound water molecule. So the reason why we talk about this is I'm getting choked up. Let's say I take something like sugar or Kool-Aid, and I bind that, and I pour that Kool-Aid into a thing of water. What's going to happen is all those sugars, all those dye particles, everything is going to bind with water. If I put a lot of sugar in there, my Kool-Aid's not that watery, and the reason why is because all those sugar molecules bound with water. But if I make some weak Kool-Aid, like your mom smacked you and said if you add any extra sugar in there, like I'm gonna smack you, hit you with the chancla. So if you drink the Kool-Aid, it's really, really watery. The reason why is because you don't have that much stuff in there to bind with the water molecules. Okay? Because on a molecular level, you remember what we said, one of the traits about water? Water acts as a good solvent. And the reason why is because I can have something like, let's say I've got Na plus and Cl minus, meaning these things dissociate. And if I've got this Na plus, I can have that water that was slightly negative, or that oxygen that's slightly negative, and I've got those hydrogens there. All right, and so that water molecule is bound because it forms this bond with this Na, all right, or this sodium. So that means it's bound. So that's actually what's going on a molecular level. It's bound to something. So it's not free anymore. It's not this young, wild bachelor water molecule that's running around looking for something to bond with. It's already tied down. Okay? So how this would look. I'm going to draw 10 water molecules on the outside and 10 water molecules on the inside. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That bugs me that I didn't draw it evenly. There we go. And then I'm going to draw 10 on the inside. And I'm going to bind these with stuff. So I'm going to say sorry, I didn't really. Oh, you're welcome. Free and bound.
Hello.
Ring, 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 ring. Hello?
Tech support.
Okay. So now you guys see on the right hand side how I wrote a free water molecule is one that has nothing on it, and a bound water molecule is a water molecule that has a solute particle on there. So on the outside of the cell, so when I say outside, I'm referring to these ones right here. On the outside, how many free water molecules do I have? 4. Cool. Ooh, definitely don't want to draw with that one. I've got, ooh, come on, you can do it. I believe in you. I've got 4. How many bound water molecules do I have on the outside? 6. Cool. All right, what about on the inside of the cell? How many free do I have? 8. And how many bound water molecules do I have? 2. Okay, so which way do you think water is going to move? Water will move here. We just got to figure out which way it's going to move. Is it going to move into the cell or out of the cell? What do you guys think? Look at the definition we have of water or osmosis. Osmosis is the passive transport of water from high free water to low free water. So on here, on the outside of the cell, how many free waters do I have? 4. How many free waters do I have on the inside? 8. So where is the high free water, on the inside or outside? The free water's on the high free water's on the inside. Low free water's on the outside. And osmosis, ooh, what the heck? Osmosis said passive transport of water from high free water to low free water. So which way do you think it's going to move? It should move from the inside out. So water should move out. You will have a very small amount that moves in, but the majority net movement of it is out of the cell. Because there's high free water on the inside. Now let's talk about this in chemistry nerd terms. Whoop! If I want to talk about a lab that brings back a lot of PTSD for a lot of people for some reason in chemistry, what was the Kool-Aid lab about? Concentration. And concentration is measured in what? In chemistry. It's measured in moles or molarity. So what's going on here is if I were to look at this inside the cell, this might be 0.2 molar. And the outside might be 0.6 molar. So which one has more stuff? The outside or the inside? The outside has more stuff. All right? Cool. So keep that in mind now because we're about to go into some nerd terms. Okay, so we're going to talk about concentration terms. It's all going to start clicking in a second. Concentration terms. So, some stuff we've got to talk about. Term number 1 is tonicity. We've got 4 words. Tonicity is talking about the amount of solute. And solute is stuff. Okay. Tonicity is the amount of solute or the amount of stuff. I'm just moving so I can see where I'm at, so I can see what you guys see. Oh, you're good. I don't want to make you nervous by sitting next to you. Okay. And then I've got tonicity. I can also have hypertonic. Okay. If I'm talking hyper, I'm referring to someone's energy level. Do they have more energy or less energy than normal? They've got more. So hypertonic means, what did we say tonic meant? It's the amount of what? The amount of solute. So hypertonic is talking about more solute. And if I've got more solute, do you think I have more free water or less free water? If I've got a lot of stuff, I've got less free water because all that water is bound to stuff. Okay? Less free water. Okay? And if we've got a word for more, we've also got a word for less. What does the term hypothermia mean? Do you know? Your temperature gets very cold, so it means your temperature is less than it should be. So our other term that we have that's the opposite is what's called hypotonic. Okay? And that's going to mean less solute. And more free water. I'm going to close that. We did it just because it's smelling. All right. Can you think of a term we might be missing, something that's comparing these? So we can have one is more than the other one is less than the other one. What might be another term that we might need to talk about? Equal. That last term is isotonic. Somebody watch the video. Same amount of solute. Same amount of solute. All right. These are our last vocab words. We're going to draw one more, and then it's all going to start to make sense. And then you're going to come up with a rule. Okay, ready? All right. So if I draw this out, let's say we've got number 2 right here and right here. And let's say on the outside I've got 1, 2, 3, 4, 5. And on the inside I've got 1, 2, 3, 4, 5. Okay, and now here I put 1, and in here I put 3. And if I were to put it in terms of molarity, I'd say this is 0.2 molar, and on the inside of this is 0.6 molar. Whoa. So 0.6 molar. This one would be blank tonic, and this would be... So these terms tonic, hypertonic, hypotonic, isotonic, those are always used in comparison with something else. So this is going to be comparing the inside of the cell with the outside of the cell. So if I'm doing this, the inside of the cell, the one with the 3 dots in it, or the one that's 0.6 molar, do you think that would be hypertonic, hypotonic, or isotonic? Okay, look back at our words. Our words, hypertonic means it has more solute. Those red dots are solute. Hypotonic means it has less solute, and isotonic means it has the same amount. So the inside of that cell should be hypertonic. Hypertonic, meaning the outside is what? Hypotonic. Okay. Now I got to figure out which way water moves. What do you think? Remember, water always moves. If we look at our osmosis rules, water always moves from high free water to low free water. Where is there more free water? There's more free water on the outside. So which way is water going to move? Water's going to move in. Cool. Now I want you to try and figure out the rule that you're going to come up with. So the rule, let's say, is water always moves from blank to blank. I want you to use those terms hypertonic and hypotonic. Talk with your partner if you need to. What do you think we would put in there for this rule? Water always moves from what? Is it from hypotonic to hypertonic, from hypertonic to hypotonic, from isotonic to hypertonic? What the heck does it move from? Water always moves from blank to blank. In this picture, what does our picture show? What did you say, Cindy? Water always, always, always moves from hypotonic to hypertonic. And the reason why is because if it's hypotonic, it's got less solute. If it's got less solute, do you remember what we said about the water? Less solute, more free water. If it's got more solute, so it goes from hypotonic, which means less solute, more free water, to hypertonic, which means more solute, less free water. Okay? So that means it's going to be moving from high free water to low free water, and that's what osmosis does. Got it? Get it? All right, I'm going to give you some questions now. All right, we're going to do some practice problemos. What about, let's say I've got 0.8 molar and 0.4 molar. Which way is water going to move, inside or outside? So if I'm solving this, the first step I would do is I would figure out, okay, which side has more solute? Which side has more stuff? Outside does? Okay. It's got a higher concentration or a higher molarity, meaning the outside has more stuff. If it has more stuff, the outside is hypertonic, meaning the inside is hypotonic. And what did we say our rule was? Water always moves from what to what? Water always moves from hypo to hyper, meaning water is going to move out of the cell. The cell will shrivel up. What about what the heck? Trick, shot, bing bong. This is isotonic. So what do you think's going to happen? Okay, so isotonic means no net movement. Okay, no net movement. Let's say I told you at lunch, I said there's no net movement of students in and out of my room. Do people come in my room at lunch?
Yeah.
Yep. Do people leave my room at lunch?
Yeah.
But then how come I can still say there's no net movement? It means for every one that leaves, one more enters. The same thing happens with this. It's what's called dynamic equilibrium. The root of this is equal, meaning it's the same on both sides. I've got the same amount of free water on both sides, and so some water is going to leave, but the same amount of water is going to come in. Because that term dynamic means movement. In sports, there's two types of stretching. There's static stretching, which are like your toe touches. So like you're bent over and you're touching your toes. You're not doing any movement. Dynamic stretching is like your high knees, your butt kickers, your A skips, all that kind of stuff. That's dynamic equilibrium. Okay? You ready for our two real life examples? Let's say mom's being nice. I know, it's rare. Okay? And mom lets me go to the pet store. And I decide at the pet store, you know what I always wanted? I always wanted my own Dory. Your Dory's ugly. For real. There's my Dory. All right. Dory is found where? The ocean. And is the ocean freshwater or saltwater? Saltwater. So we'll say Dory's got a molarity of 0.4 molar. And I didn't know any better. What the heck just happened? I didn't know any better. So I took Dory home and I just thought all fish did well. So I put her in freshwater, which is 0.0 molar. Guess what happens to Dory? She did.
I was gonna do that with starfish.
Okay? I just thought I could put any fish in water because, you know, it's a fish. What difference does it make? So, she's dead. I want not shrivel or swell. Did her cells shrivel or burst? What do you think? Did Dory's cells shrivel or burst? Why do you say
It
burst?
shriveled. Did it shrivel?
You tell me.
Oh, I thought you were saying it was wrong.
No, you tell me. She did. She a heck of a floater now. She may not swim too well, but she can sure float. Okay. Dory going straight to those float Olympics. Okay. So, what do you think? Did her cells shrivel or burst? First off, where is hypertonic? Dory or the water? So we'll say Dory is hyper. What the heck is going on? We'll say Dory's hyper. Well, she's not too hyper because she did. So Dory's hypertonic. What about the water? Is the water hyper or hypo? Hypotonic. And we said water always moves from where to where? Hypo to hyper, meaning water's going to move in, meaning her cells will burst. Because Dory is an animal cell, and unlike plant cells, what does Dory not have on the outside of her cells? She doesn't have a cell wall, meaning if too much water gets into her, her cells will burst. That's why you cannot go to the hospital and get an IV that's pure water. That little bag that's hanging above you at the hospital, all right, that has clear liquid in it, it is not pure water. If you gave someone an IV with pure water, it could kill them. Because you're going to have pure water on the outside of your blood cell, and it's going to cause your blood cells to burst. Okay? Problem? What? Last one. Okay. I'm going to draw a nice landscape. Oh, not that. So, what I've got here, let's pretend that this is Canada. All right. So, I've got Canada, and one thing about Canada, it gets very cold in the winter, and where it gets very cold, they have snow, and where they have snow, they have ice. Ice is bad news bears if you're trying to drive. So, I've got right here a road. And do you know what they put on icy roads? They put salt on icy roads. And right here, I've got dead plants. And right here, I've got happy trees. But it's happy trees. Okay. How come springtime, when all the grass is growing back and I've got happy trees and everything, how come the first foot or two right next to the road, everything is dead? Why do you say it shrivels? Okay, because what I have done is I have taken that road, and on that road to melt the ice, I put salt. Salt is very, very, very hypertonic. And so when that gets next to that plant is hypotonic. It literally sucks all the water out of the plants that are next to it, and it dehydrated all of those plants that are next to it, and it killed all of those plants. Another way that this happens all the time, and some of y'all need Jesus for it, is not Dory. So you've probably never done this to Dory, but poor Gary over here. Okay. Some of y'all who are jacked up, what do people put on snails? Salt. And do you know what happens to the snail now? Okay. It sucks all the water out of the snail and kills it because you literally dehydrated that snail by sucking all the water out of it. Okay. So you killed the snail by creating a very, very, very hypertonic area on the outside. Hey, cut the talking, guys. We're almost done. Okay? You create a very, very hypertonic area on the outside. That snail becomes hypotonic, and now you literally sucked all the water out of it. You dehydrated that snail, and you killed it by doing that. Another way that this works, we're almost done. We're talking about examples. Let me draw this. What do trees need? And how do I get a tree to drink? All I literally do is I just put water right here at the roots because the roots absorb it. And now the reason why is because this tree is hypertonic, meaning this free water is hypotonic. So that water goes from the water straight into the tree. It absorbs that in there because that water is hypotonic, that is hypertonic. Another thing that you might have done that killed it, some of your homework, summer homework. Did anyone give their plant other types of liquids?
Coffee and
decided this.
Okay, you gave yours tea. How'd it work?
Better.
What?
Yeah, better than water.
All right.
I'm just saying. No, mine, it was better.
A lot of people took their leaf. All right. Let's say I've got this leaf and I give it like Coke. Not cocaine. I give it Coca-Cola. Okay. What happens is that water killed the leaf. It killed the plant because now that Coca-Cola, this became hypertonic. This became hypotonic. So it literally dehydrated your plants and it killed them. So if you tried to water it with something else, it dehydrated your plant and killed it. That right there is the same concept of why plants die on the side of the road in icy climates. Not that you care, but now you know. Okay? Questions? Comments? Concerns?